Hello, so I'll be talking about Lab 4, Oscillations. And first of all, what my presentation consists of is the introduction, where I'm talking about the purpose of the lab. Then I'm going to be discussing the equations and formulas we're going to be using throughout the lab and plugging into the code. Then I'm going to be looking at the initial values, the observed data from the code, and then the closed script code, and pretty much analyzing and understanding it. And then I'm going to be answering the discussion questions while summarizing the content. So, what is the purpose of this lab? So, we're going to be predicting the motion of our system with a spring and a mass. And through that system, we're going to be demonstrating the fundamental principles, which are the Newton's second law and the energy principle. And our system consists of a mass, spring, and the earth. And we have no surroundings, which is very, very important to note. And so the fundamental principles that we're going to be using are the law of conservation of energy, which is pretty much that the change of the energy of the system is the work done by the surroundings, plus Q. And Q is not essential here because we're not going to be discussing it. So we're going to conclude that the change of energy is zero, and we're going to later discuss that more. But the potential energy formulas are these, and this is the kinetic energy formula, but these are the potential energy formulas we're going to be using. And we're going to be using also the kinematic position and velocity equations. As our object is moving, we're going to be tracking its position. And so for our case, the initial conditions here are that there's no work from the surroundings, so there is also no Q, so it's safe to assume that the change of energy is zero, as the initial and final system has the same energy as it has been preserved. So that gives us this. And then this is pretty much our system. This is a force body diagram, and the force of spring has the opposite direction of the force of gravity, but they are opposing each other and balancing each other, which means that the magnitude of those is of the force of spring and the force of gravity is the same. So we can conclude this. And this is our tracker video. This is the system that we are observing. We can see that the object is moving in oscillations. And so let's look at the code. So this is our code. These are the initial values that we know. The mass here, the position of the ball, and then the force of the acceleration due to gravity, which is obvious, and then the stiffness, which can be observed through the CVS file, and also the initial information can be seen in the pre-lecture video, and then the free length of the spring, relaxed length, which is 0.123. And so in this part of the code, we're pretty much looking at this equation. We're looking at S, which is this, and then we're going to be looking at the different energies, the kinetic, the two different potential, which is pretty easy to understand here. And then the final equation is pretty much the total energy is equal to all these three added together, which is zero. The change of it is zero. And then the time of movement is this, which was already given to us. And then the force of gravity can be seen here in the code. The force of the spring can be seen here. Then the F net is pretty much force of gravity plus force of spring, which is here. And then we're also looking at the position and velocity, which can be used knowing these formulas, pretty much just converting them into the code format. And then this pretty much means that each iteration goes as t is larger or equal to 6.648. So this is then what we get. So this is pretty much like one iteration. And yeah, this is what our code produces. And so these pretty much cancel each other out. We see that this here down is equal to this here up is equal to this down, and same goes as red. Pretty much cancels the negative here and the positive here. They cancel out, which proves that the system change of the energy in the system is zero. And so these are the x and y graphs. And so what are potential errors that can be spotted? So air resistance can cause a potential error, or miscalculating the initial velocity. It might not start from 0, 0, 0. And also incorrect delta t interval can also be computed in the wrong manner, which are the potential errors. And so is the energy principle satisfied? Yes, as we already discussed, like these cancel out each other, which causes that change of E to be zero. And this satisfies this equation then. And also in the x graph, we can see that the oscillation period is from 1.6 to 1.7 seconds. And Here in the y graph, it's exactly 1.5 seconds. And so why is it then important to look at the two graphs for the oscillations? Is because, as we see, the oscillations can be different values, so it's good to look at them from both graphs and then estimate the average. And that's it. Thank you for your attention.